Okay, there are going to be three things that we're going to take a look at for charge distributions and electric fields. So yeah, I'm going to do the first one linear now, and then I think I'll make two other videos for the other semicirculars and plates. The key thing that we're going to do here is we're getting into calculus, and in calculus we want to have only one variable, so only one thing changing at a time, and then we can integrate or derive whatever we need to do. In this case, we'll be integrating. So our challenge with the math is going to be to get down to a single variable that's changing. So one of the keys that we have for this is using density, and we're going to use one of these three. So linear charge density, surface charge density, or volume charge density, and in the first case, we'll use linear charge density. So notice the density is going to be consistent. So I'm assuming two things. I'm assuming the charge is distributed evenly and that it's a uniform shape. So wherever I look, if I have the same small fragment, I'll have the same small amount of charge. And so I can rearrange my linear charge density Q over L into a dQ, so that small amount of charge that's in some dL, some small amount of distance, right? And so notice that my density won't change, so I still have the same density, and I can replace that density with with my known quantities, capital Q over my total length. So this is what we're going to do. We're going to use density to help us get rid of that small amount of charge, and it's going to be very similar for many things that we do. So we're going to use some form of density to help us get rid of something that's changing that we don't want to deal with. So I'm going to have some distance here. I'm going to have some bar here, and it's going to have some line of charge in there, some charge here. I don't say it's positive charge, but it's positive, 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 positive. It's going to be all over in here, evenly distributed. So I know my linear charge density, lambda, is going to be Q over L, and I can write this as dQ over dL. I might write this as a dQ over dx just to say, so I'm going to use distance, right? So remember what I'm doing here. So I'm taking this small piece in here, right? So this is some small thing, it has some distance, so dx that is being covered, and it's going to have some small amount of charge that's there, dq, and I can find I can use the linear density to switch between those two. So what I'm interested in, there's some distance here that I want to find. So here's the point I'm interested in. So I'm going to get this P as my origin. So I'm interested in what's the electrical field at this point, and I'm going to add up. So what's the electrical field contribution from this? Well, remember my electrical field generally is force per charge. But for a point charge, and if I make this small enough, I consider this a point charge, right? That small amount of charge is going to be some constant K times some small charge over the distance, the square of the distance, right? KQ over R squared. Right? So I could get some small amount of my electrical field. So my small amount of electrical field is going to come from that small amount of charge, dQ, divided by that distance here. I'm going to say, that distance here is going to be x squared, right? So now what I want to do is I want to turn this into something I can integrate and add up all those small pieces. I'm going to be careful here, right? So I'm going to say this has some length is equal to L, so I'm going to add up from A to A plus L. From A, I'm going to A plus L. So I'm going to figure out the total length. Right, so the challenge here, though, is that small amount of charge is changing, and yeah, my distance is changing. So I got two things changing here, which is going to be a hassle, so that's where my density is going to come in. So I'm using linear charge density to get me from out of this hassle of having two things changing. Right, so I can write this, my small amount of electrical field is going to be a function of some constant times that small amount of charge, which is lambda times that small amount of distance, divided by my total distance, right? So now I've got something I can make sense out of, right? So I have one thing changing, I have 1 over x squared dx, and I can add those all up. So what do I want to do? So I want to get to my total. My total is going to be the sum of all of these, and I'm going to go from A to A plus L of k lambda dx over x squared. Right? Okay, now I got to do a little bit of math. So I want to evaluate my integral. So it's a definite integral, so that helps. But yeah, so I have some constants. Let me pull those out. So k and lambda are constants. I'm going to pull those out. So E is going to be k lambda times the integral of A to A plus L of what? Well, I'm going to write this instead of 1 over x squared, I'm going to write this as x to the minus 2 dx. So I want to integrate something to the, so what do I do? This is a power, so it's a reverse power rule, right? So I'm going to take this, I'm going to add 1 to the exponent and divide by that new exponent. So I add 1 to the exponent, I get x to the minus 1 now. I divide by my new exponent, and it's going to be a negative. And I multiply this by my constant still, and I want to evaluate this from a to a plus L. Right? And this is going to be, right. So, and now I'm just doing a little bit of math, so I want to get to, I want to have this subtract that from it, so this is going to be k times lambda times this, so I'll say negative 1 over a plus L, and I'm subtract from that negative 1 over a. Right? So convince yourself that makes sense. Right? So my final minus my initial. This is going to be a positive, this is going to be negative, so I can rearrange this to make this a little bit easier. K lambda, it's going to be 1 over a plus, this was this 1 over, no, minus, it's 1 over a plus L. Right? And I'm going to end up with a, with some simplifications that I can do. Right? I can simplify this as shown here, right? So I multiply these two together. So I want to simplify a fraction, so I'm going to have a over L times a over L. So I've just multiplied top and bottom by a over L. And I multiply top and bottom by a, so it's minus a over a times a plus L. All right, so simplifying my fraction. And multiplying by k lambda. Let's see, so this a is going to go, it's going to cancel here, so I'm going to be left with just with L, right? So this is going to be equal to k times lambda times L over a times a plus L. Well, I'm close, right? But I still have this linear charge density, right? And yeah, that's I don't really want to have that in there. But remember, my linear charge density I use to get here, but it also, that density is going to be true for the entire rod. Right, so my entire rod, my total Q divided by my total length is also equal to this. So I can replace my linear charge density with the constants that I started with. So I started with Q and L. So I can replace a linear charge density. So this is going to be K times Q over L times L over a times a plus L. All right, so notice one of my L's cancels, so I'm left with KQ over this thing, which is a times a plus L. Well, let me think about this. Does this make sense? Well, what happens if I get really far away? So if A is very large, then L becomes inconsequential, and I'm left with KQ over my distance squared, right? So KQ over R squared. So it acts like a point charge when I get really far away. So hopefully that makes sense, and it's consistent with this. So this is a way that we use linear charge density to be able to get to the electrical field when I'm at some distance from a rod like this. Anyway, I hope that's helpful, and we'll move on to different shapes and look at electrical fields from different shapes.